All right, so if you all have folks in Florida, our thoughts and prayers are for them. You know, some of you come from that part of the world, you lucky dogs. We will not meet on Monday, remember it's Labor Day. And so the topic for today are these two items shown on the board. I probably won't speak very long this morning because I just realized I only brought 4 sheets of paper, so everything has to fit on 4 sheets of paper. Okay. We've been talking about the step response, estimating the step response without having to do a lot of math. Okay. Remember, we use transforms, Laplace transforms to describe transfer functions in this course, and we would really like to minimize the math we do. You know, we avoid calculus by going to transforms that give us algebra. But we'd like to be able to quickly identify the response of some basic models. So we talked about first order models and second order models. And so the first topic today is really a little bit of a review. I want to kind of, again, remind us what is the relationship between this transform world that we call the S-plane. Some people call that the frequency domain or the S domain. And how does that relate to things that we understand in time? So we've looked at this over the last few days, but I just kind of want to briefly review it again this morning. And then I want to talk a little bit of time, talk a little bit in the time remaining about some practical issues that we often face. In reality, most things that we deal with in life cannot be so simply modeled as first and second order. And so they're going to be more complicated. And so these are practical issues, and I just want to talk a little bit about those things. So those are those two items right there. Let's turn our attention now to the first topic, and that is the relationship of S-plane poles to transient response. Okay, so we're going to talk a little bit about the transfer function. Again, remember, a transfer function is a model that describes the input-output relationship of something, and a typical transfer function is going to, the ones that we've looked at are first order, so it could be like this, or second order. I'm going to turn autofocus off for a second here so that it quits trying to do all its work. The second case is second order, something like this. And we talked about at length about this funny Greek letter, omega ns plus omega n squared over omega n squared. Okay, so we looked at those two forms. And what I'm saying is we want to kind of reinvestigate these denominators. We call those the poles. Okay, there are more complicated models, and we'll talk about that in a minute. These are the two basic forms that we want to at least be able to quickly sketch their response. And so in the S-plane, let's first take a look at the case of first order system. For all systems, regardless of their order, what we want to do is we want to remember is that we don't allow any poles over here in what is called the right half plane. So this is the real axis, and this is the imaginary axis. So basically, this is in the plane S. Okay, this is not time. This is imaginary and real parts of this variable S. And so first off the bat, we don't allow anything over here. So we need to concentrate on our responses, as the poles are in the left half plane. So one of the things that we'll remember for the first order case is that we have a pole here, somewhere in the left half plane. It's related to this number tau. It's minus 1 over tau. And so the response of the system is going to be an exponential function, e to the minus t over tau. And so if we were to kind of draw a sketch, I'm just going to put a little sketch right here. This is now in time. I'm just going to put a little cartoon here in time. The impulse response is going to be an exponential function like so. Okay, or the step response will be something that settles out at some non-zero value. So this is e to the minus t over tau. Now, if the pole is further over this way,
what we see in the response is something is still an exponential, but it decays more quickly, like so. It's still e to the minus t over tau. Maybe we'll call this one tau 1 and call this one tau 2. Okay. So the idea is that the further over the poles are in the left half plane, the faster the response. The closer the poles are to the imaginary axis, the slower the response. So that's the first order case. This is the relationship between S-plane locations. This is the S, and I put two little more graphs in here, but these are in time, and this is the time response. If we do have poles over here, the response is going to be unstable, and so the response will blow up. Instead of decaying to zero, they blow up, and the further they are over in the right half plane, the faster they blow up. Okay. Now let's take a look at second order cases. In the second order case, again, this is the S plane, this is the real part, and this is the imaginary part. Okay. This form here basically is going to be a couple of poles. It's going to have poles that are complex conjugates, as we mentioned before. And so that means the real parts will be the same, and the imaginary parts will be opposite in sign to each other. So it's symmetrical about the real axis. Okay? And what we'll do is let me sketch a few different locations. Here, let's suppose that associated with this type of set of poles, what we know is that we get some sort of exponential envelope, a decaying envelope, because things are in the left half plane. And so we have this type of behavior, but because there's imaginary parts, there's also kind of there's a sinusoidal behavior. So the impulse response will look something like this. We'll just try to squeeze a sinusoid in there. Okay. Now, if we have poles, say further out like this, further away from the real axis, they're more imaginary, and the real part is also a little bit slower, then what we're going to do is we're going to draw a slightly different picture. Let me draw that picture here. These are pictures in time now. The decay will be slower. It'll be more gradual. Still decaying though. But because I'm further up on the frequency axis, imaginary is the frequency axis, the omega axis, the frequency will be higher than for this case. If we were to put them poles, say, further over here, where the real part is much larger, but the imaginary part is smaller, then when I sketch the response, the impulse response, I would expect a faster decay, something like this. I'm going to exaggerate like this. And the frequency is going to be lower, so it might do something like this, kind of like so. Okay. So let's see if we can kind of group things. This set of poles is associated with this time response here. Okay. This set of poles is associated with this response here. And then finally, this set of poles is associated with that one. Okay. So this one page of notes is trying to summarize the relationship between this language called the S domain, these marks in the S domain, and the transient response, the general nature of the transient response. Now, as I said, these transfer functions that I show here are what we call the most basic, simple, standard forms. You can easily come up with models that have things in the numerator that are functions of S, and that complicates things. And so that means that these responses get scaled. The general nature is still the same. If I have some term up here that involves an S, the general nature is going to be the same, but in the sense of decay and frequency and stuff, but the scaling will be a little bit different. Okay, so the two topics today were relationship of S-planes, poles to the transient response. And then now, let me pause there for a moment before we turn our attention to the second topic, the more complicated
practical issues, the issues that we get paid money for. Okay, any questions?
All right, let's move on and talk about more complicated practical issues. One of the practical issues is what if the model is not in standard form? Okay, practical issues, again, are the things that are meaningful in life, and it usually means that we get paid for them, which usually means that they're more difficult than we see in the textbook. Okay, the things that get in the textbook are only good for giving exams. You pay me to give you exams. But one day, somebody's going to pay you because you're a good engineer. Practical issues. Okay, how about things that don't fit the standard form? Okay, models not fitting a standard form. The standard forms that we have are just two of them: the first order case and the second order case, specifically this case or this case. Okay. As an example, suppose I had 10 times s over s plus 2. Okay, that doesn't fit the standard form. I can't squeeze it into a standard form. Now I could try to get it close. For example, I might divide top and bottom by 2. If I divide top and bottom by 2, then I get something like 5 over s, 0.5 s plus 1. Okay. That's still not standard form. But what I can say is maybe this kind of looks like s times 5 over 0.5 s plus 1. Okay. And so what we might remember is to say, let's break this up into parts that we understand. And this part looks standard form. It fits the standard form k tau s plus 1. Okay, so I can sketch the response of this part. Okay, I can sketch the response of this part. This is now in time. Let's review a little bit what we remember about the response of first order systems here. So here the time constant is 1/2. So the settling time is going to be roughly 4 times that time constant. So that'll be 4 tau is approximately 2 time units. Okay, so this response will settle on 2 time units. And the gain here is 5, and so I would expect the response to settle out to whatever is 5 times the input. 5 times the input. So I would do a sketch something like this. This is only this part of the response. But we have a model that looks like this. So what we would have to do is let's break up the problem into something that we understand. We understand how to do this part. Now we have to ask ourselves, do we remember what it means to multiply by something by s? Multiplying by s in the transform domain, in the Laplace transform, what does that mean in the time domain world?
Convolution.
Convolution will kind of move in the right direction, but it's a little simpler than that. Remember, why do we go to S domain? Because we want to avoid calculus, right? So multiplying by s is an algebra operation in the transform domain. In the time domain, what is the calculus operation that's related to multiplying by s? Derivative. So really, this thing is the derivative, right? So we got to ask ourselves, what is the derivative of this?
So overall, we can remember that this means differentiation in time. So we might try ask ourselves, we could sketch the derivative of this function. The derivative of this function might look something like this. Okay. It might take a little bit of time to think about what is the derivative. Derivative is the slope. What is the slope here? Some positive number, right? So I pop out here.
what is the derivative out here? It's getting flat. So it makes sense that it's getting the derivative is small. So this is the derivative of that. The exact details, the scaling, and all that sort of stuff will have to be worked out. Takes a little bit more time. Okay, you have to tell a customer, I can't do this over a lunch at Chick-fil-A. I need to go back to the lab and do a little bit of study. It will cost you more. Okay? So instantly, the problem becomes a little bit more complicated. You could probably sketch out this part, the black line here, real quickly over lunch at Chick-fil-A. Because it fits the standard form. We can do that real quickly. That's why we can put it on exam 1. Because you can do it within 10 minutes or less, 5 minutes even. Right? That's what our expectation is. But this problem is a little bit more complicated. So what's the ideal? Every good engineer takes a complicated problem and tries to break it apart into things that they understand. We understand this looks like a standard form, and we understand this multiplying something in transform domain is equivalent in time domain of doing a differentiation. Okay, so that's one example of something that is not fitting a standard form. Maybe I'll give another example, example number 2. Okay. Example 2. Let's suppose I have a model s plus 1, s plus 3 over 3. Okay. I compare it to my standard forms that I know so well. It's certainly not that one, because it's got 2 terms that involve s, and it doesn't quite look like this either, okay, because I don't have complex conjugate poles. I have 2 real and unequal poles. Okay. So again, let's try to break this up into something simpler that we understand. Let's break it up. One way to break it up is to break it up into the sum of 2 parts. This is the same thing as something over s plus 1 plus something over s plus 3. From an algebra standpoint, does this look reasonable? Something with one denominator plus something over the other denominator, I could find common denominators and somehow combine them, and it turns into something that looks like this. Okay? Most of us remember how to do this. We'll go from this way to that way. It's an each algebra. But now there must be some sort of algebra that goes from this way to that way. Okay? So most algebra operations can be undone, just like multiplication can be undone by division, addition can be undone by subtraction, combining terms to find common denominators. How it can be undone this way. We just have to go to the font of all wisdom and remember how to do that. The font of all wisdom, of course, is Google. Okay? It's amazing what you can find on Google. I think a person can do a PhD these days in probably 1/4 the time that I used to do. When I was in graduate school, you had to find out what is the latest going on in research, and so you wait each month for something to appear at the library in regular mail. It's one copy of the Journal on Electrical Engineering Advances in whatever field. And you get up early in the morning because you want to be the first one at the library to get that copy, because there's 150 other graduate students who also want that copy. And that's what drove me. Now, you put a Google search, and everybody has it. So, but it still takes graduate students 4 years to earn a PhD, or 3 or 4. So, how do I go from here to here? Anybody remember what that operation is called?
Partial fraction example.
Oh wow, this is a bright bunch. Partial fraction expansion. Okay. I grew up in the hills of East Tennessee. I certainly did not know what that was called. We were dirt poor kids running around in the hills with no shoes. I went to graduate school to learn this thing. This is called a partial fraction expansion. All right. you have to find out what is that numerator, these numerator terms. Okay? Now, the way I remember to do a partial fraction expansion is, I say I want to know what is at the top of this. So I multiply my original model by s plus 1, so I cover it up. I multiply this by s plus 1 to basically cancel this out. And then I let s equal to minus 1, okay? So when I put in s equal to minus 1, I get 3, and this is hard. I have to talk and write at the same time. And I have to do a harder operation, it's called division. So it's 3 over minus 2, no, 3 over plus 2, so it's 3 halves. Okay? So look at all those different ways that even a simple algebra could trip me up. And then to find the thing over here, what I would do is I take the original model and I multiply by s plus 3. That basically eliminates this term. And all I'm left with is that or that. But now I let s equal to negative 3. And now I have 3 over negative 3 plus 1. Negative 3 plus 1 is negative 2. 3 over negative 2 is negative 3 halves. And if we've done our math right, supposedly combining these two ought to give us that. Fortunately, problems like this are aided these days by computer tools. I don't know if your calculator will do it. I know MATLAB will do it. MATLAB can find these things. These are called residues. It comes out of the complex algebra arithmetic. If you're looking for some sort of technical elective before you graduate and you're kind of mathematically oriented, take a course called complex analysis. S is complex numbers. In general, it's a complex number. And so in the world of complex numbers, there's this thing that you can learn about called residues. And MATLAB has a command called residue. You can feed it the model and it'll tell you what the residues are. But what I did is this kind of hand wave. But now, each of these things looks like a standard form. This looks like a standard form, and this looks like a standard form. I could sketch the response of this standard form. I could sketch the response of this standard form. And then what do? Kind of combine them, add them together, right? That's what that means. But again, it's going to take time. So this now looks like a k1 over tau 1 s plus 1. And this looks like a k2 over tau 2 s plus 1. These are all standard forms that I can deal with. Okay. So I've taken a more complicated practical problem, broken it up into parts that I feel like I can get my hands around, and then I'm going to try to combine the results. Okay? Perfect opportunity for teamwork. I don't know how to do this, so I'll go find a friend. I'll do this part, he'll do that part, and we'll get together after lunch and we'll try to add these things together. Okay? There's a joke about how many guys does it take to sweep a sidewalk. It's not a very difficult job, but I guess we can say how many engineers does it take to get the response of something. These jobs aren't difficult, but it takes a little bit of time. All right, here's another practical issue. Maybe the system that I'm working with is not stable, cannot be tested. Okay. So an example of a system that is not easy to test is a practical example is a DC motor. DC motor, the input is voltage. Maybe I'm using this motor in a robot. Okay, I want to make my robot move. I'm interested in going from this position to this position. I'm going to move the arm with an electric motor. And so I'm interested in applying voltage to the motor windings and causing it to start turning. And the output is position of the shaft. I bolt the shaft into an arm, and now I can move that arm. So DC motor might be my process. This is not a stable model. Let me explain why it's not a stable model. Let's draw a block diagram. The input is voltage. The output is, let's say initially, is speed. Okay. We've all experienced this. How many of you drove to work this morning? Drove to class? Okay, a few of you. Others to Tiger Transit. A few of you are paying probably high buck rent and just for the privilege of being within walking distance. My dream before I die is to be able to get a house on Gay Street in town. I don't think it's going to happen because those teeny little cottages are $500,000 and up. This is the price of living, of being able to live in walking distance of work. I gotta live further out. So I gotta hop in my car and I gotta start it. I turn the key, I apply voltage to the starter. What does the starter do?
Turns over the motor.
The speed goes from 0 to something, right? So it goes. So I would expect then, when I apply a step voltage, that the speed of the motor will go something like this. This is in time. Okay, I apply step voltage, 12 volts, typically. And then the speed picks up like this. What kind of model does this look like would fit?
First order.
First order. So we would say this is a first order model. Okay. What we're doing right now is not analytical modeling, which analytical modeling says we will get into the science and the physics of the motor and the magnets and the winding and the currents. That's all EMAG study, which is hard. I bow down to Professor Wentworth every time I see him because he's an EMAG guy. And Professor Riddick, EMAG's amazing. You can't see the electromagnetic waves and stuff like that, but we can do amazing things like talk on a cell phone. This is not analytical modeling. This is empirical modeling. I put in an input, I get an output, and I say, that kind of looks like it'll fit a model like this. So I'm just going to fit the data to a model. All right, so this would be a model. I don't know K and I don't know tau. But really, I'm interested in position as output. So what is the relationship between speed and position? What do I have to do to speed to get position? What mathematical operation? I got to integrate, right? I got to integrate speed to get position. So I need to draw another block. The output of this is now position. What is the symbol I put in here? What's the symbol for integration? 1 over S. Okay. So now this is my model of the DC motor. What is the position doing here in time if the speed is constant? It's going bigger and bigger and bigger, right? If the motor continues turning, its angular position grows. So it goes something like this. So here is my model of my motor. Bounded input, bounded, right? Because it's bounded by 12 volts. What is the bound over here? It's not bounded. So this is not bounded input, bounded output stable. It's unstable. And in fact, when I combine all this and look at the model, I say, hey, I have a pole at S equal to 0. Where is 0 in relationship to right half plane and left half plane? Where is 0 in relationship to right half plane and left half plane?
Between.
It's borderline. It's marginal, right? So is that stable or unstable?
Metastate.
Okay. You know, we use the expression marginally stable. Young lady? He's asked you for a date this weekend. But this man over here says, hey, Did you know that he's marginally stable? What is your reaction? Thanks, but no thanks. Right? Marginally stable is not bounded in with a bounded output stable. And of course, you're going to go and say, "You liar! How'd you tell her that?" Okay. So this is a practical problem. The system is not stable. It's not easy to test. I cannot put in a step and get a bounded output, and I cannot find these things. So this is what we do. One thing that we can do is we can say, let's put this thing in a feedback model, in a feedback configuration. I'll go ahead and set up my robot. I'll build it. Okay? This is desired position. This is actual position. I get the error. Then I maybe multiply by some gain like this. Let's call it, not this K, but a different K. Let's call it K the compensator, KC, like this. Now I test not the motor, but I actually put it into my application. I test my application as a whole. I put a step over here. I don't put a step right here. I put a step right here. And I take a look at what is going to happen. Now, the question is, will this model be stable? Let's, instead of talking about it in this abstract manner, let's ask ourselves, will this system, closed loop, be stable? If it's stable, then I can do some testing on the system. So let's put some numbers in just so that we can do some math today. I'm going to just draw it again. Let's suppose this is 5, 2 over tau s plus 1, 1 over s. Okay, this is the output position. Let's call it theta. This is the desired position, theta desired. Let's find the transfer function between theta and theta desired. The transfer function is a ratio. It's a ratio, not in time, but in the S domain. And we've learned this week that we can find the model of a feedback system. It's forward gain over 1 minus the loop gain. So here I'm going to get, let's multiply everything. This tau, let's give tau a number. Let's say it's 3. Okay, so we don't have no symbols anywhere, just all real numbers. Okay, so what I have, the forward gain here is going to be 5 times 2 over 3s plus 1 times 1 over s. And then I have to say 1 minus the loop gain. The loop gain in this case is going to be, I've got a minus sign. Let's start anywhere. Let's start right here and go work all the way around the loop. I got a minus sign. I've got a 5. I got a 2 over 3s plus 1. I got a 1 over s. Okay. I clean up the math a little bit, and this is 10 over 3s squared plus s plus 10. Now the question is it stable? Well, I can test this, and I can check the roots, plug it into my calculator, and find out if it's stable. Okay, so it is stable. Okay, so how does this help me solve the problem? How does it help me solve the problem of finding the model of the motor? So this is what we can do. Fit a model to the closed loop system in feedback, then work out the unknown. By algebra.
Okay, so let me go back to an abstract idea, an abstract description of the problem. So I'm going to construct my application, my robot arm. I'm going to actually construct the robot. And here's my plant. I don't know what it is. I do know that it's unstable by itself, but I put it in a feedback system, and now the system is stable. And this is the output, and this is the desired input, the reference. And what I do is I fit a model to this closed loop system. I'm going to call that M of S. I have M of S in hand. I have M of S in hand. I fit a model to this. And what I mean is I also know that M is equal to, in this case, 4 gain divided by 1 minus the loop gain is K times G over 1 plus K times G. Okay, so this I know. This I know. I don't know G, but I can work it out by algebra. I can work it out by algebra. Work out the unknown by algebra. Let's do a little bit of algebra and see what we get. Let me multiply both sides by this, and I get M plus KGM is equal to KG. Okay? I know M, I know K, I know M, I know K. I don't know this, and I don't know this. But I can do algebra to isolate the unknown on one side and put everything else on the other side. Right? I can do that. So I can say KGM, again, I don't know that, minus KG, I don't know that, is equal to, let me do my algebra, minus M, move. So I can factor out the G. I'm going to factor out the G. I'm going to also reverse signs a little bit because I don't like minus signs. I try to be positive in life. Okay, so I just reverse the order of these two terms and change the sign on this side. And now I can solve for G. G is the unknown. And everything on this side is known. Okay, I do a test. I fit a model to my system under test. So I know M, and I can construct M over 1 minus M, and I built the system so I know what K is, so I can figure it all out, and then figure out what is the unknown model. Okay, this is an example also of kind of applying what we learned in kind of in reverse. I can ask the question, if I tell you this and this, this and this, can you tell me what is the overall model? But a lot of times, maybe we have to go in reverse. I do an experiment on the overall model, so I know the overall model, but there's bits inside that I don't know how to do. I don't know the details, so I'm going in reverse. Time? I've got
9:40.
10:42 on my watch.
9:41.
So I'm ready to call it a day. Anybody else have any objections? Okay, seeing none, let me kind of briefly review what have we done today. Just looking over a few sheets of notes. We kind of reviewed the relationship of S-plane poles, the S-plane language to real life, life and time, and then we'll talk a little bit about some practical issues.